All right. Let's start our third series of lectures by Anders Sandvik from Boston University, who's going to teach us about lattice models and numerical simulations and applications. Thank you very much for coming.
All right. Well, thanks a lot to the organizers for having me. So, I guess with lattice models, we move a little bit closer to reality in terms of, modeling materials and so on, than with the field theories. But of course, my goal is to, try to connect these two sorts of approaches. So let me quickly go through my outline. I sent you this, I don't know if everybody saw it, but the abstract and outline of my talks, and I think I was a bit overambitious, when I wrote that, so we may not go through everything I mentioned there, but I do want to give some, introduction to models and their experimental motivation before moving to, looking at actual numerical simulation methods. But, the people use all kinds of methods. It's a wide field, and I'm not, of course, going to cover everything, and it's of course heavily biased towards what I'm using myself and so on. Okay, so then my goal, as I mentioned, of course, would be to connect to quantum field theories, and then the way we do that is through finite size scaling, and that can give us the scaling dimensions that you have in RG. Okay. So then, after going through, methods and so on, I'm going to talk about some applications. And maybe the sort of main application I will get to would be on deconfined quantum criticality, which it was mentioned already here today, and I suspect there will be more about that from the field theory perspective. So I want to show you what we can do numerically on that front. Okay, but as I said, I think I was a bit overambitious in terms of what I mentioned in what I wrote down. I do want to try to cover all of these, but they will not be as separated into four different categories here. So there will be applications, also spread out, even in the more introductory material. And also, I'm not going to really talk about technical details, how to do, various numerical simulations, because if you really go into the details, it becomes quite complicated, and I think also it becomes, less interesting for people who are not actually planning to do that. But nevertheless, I will try to give you, the principles of a few different methods without giving those technical details. So, focusing on principles and the capabilities of those different methods. What can we do with them, and, giving you some illustrative examples, including, very recent examples, okay? Now, I have a lot of slides, and in some cases I may not talk about, all slides in detail, even though there's quite a lot of material there. So the intention of that is that, those who are really interested can, look at some slides in more detail later on. I will talk about most of what I have in my slides. Okay, so, one of the overambitious things was, in my outline, I also mentioned maybe something on spin glasses, but I suspect I will not have a lot of time on that. And I guess the field theory discussion here will not be so much focused on those. Anyway, all the disordered systems were mentioned, by Chong Wang. There was a question about those. So I will talk about some disordered systems, in fact. Okay, so why do we study quantum lattice models? Okay, maybe everybody has some idea about that, but let me give you, some perspectives that I have here. So, of course, one is to model materials, but there are many different kinds of materials. So one would be, what we call strongly correlated electronic materials. and a subset of those would be quantum magnets, where we only study the spin degrees of freedom of insulators. And in fact, that's what I do most of my time, so I will also focus these lectures mainly on quantum spin models and give you some motivations from materials where those actually can be used. Other systems that people study these days is, trapped atoms in optical lattices. That's a big field that I will not really discuss. Now, an emerging field is, what people call quantum emulators, which are some sort of programmable devices where you typically have spin 1/2 degrees of freedom and they are coupled to each other. And the intention is, at least one of them, to try to, model some actual, material or quantum system as a sort of analog quantum computer. Okay, so that's one area. Another is, just the models themselves can be used to explore new physics, right? Physical phenomena. So we can try to construct minimal models to, capture some known, interesting, or maybe unknown, some new phenomena, without, distraction of a lot of details that you have if you really want to, model some specific real material in all its gory details. So, for example, we want to characterize, various types of ground states and excitations, especially those not described by conventional quasiparticles, and quantum phase transitions, exotic ones like deconfined criticality, which is supposedly beyond the LGW, Landau-Ginzburg Wilson paradigm, although I start to have some, questions about that, as you will see later on. I mean, how much outside is it really? Okay, other applications as well. Now, in the context of this, training week here, I really hope I can at least give you some sense of how we can, connect to what people do in field theory. Actually, let me ask you, if you are more, numerically inclined than theoretically inclined, raise your hand. I just want to get a sense of what. Okay, so nobody's really numerically inclined, but maybe a little bit. Okay, so some hands are slowly going up there. And anyway, so then it's probably really a good thing that I don't do too many technical details, but again, hope to give you an impression of what can be done and, maybe convert some of you to the numerical side. Okay, let me first tell you about something that I will not really talk about at all, what people call, ab initio methods, which are, where you treat electrons as weakly interacting quasiparticles and you calculate band structures and effects of those weak interactions. So there's lots of software packages available for those. Here's some just example from one of those, the band structure of silicon, and you can see that two different methods are compared here. So these approaches normally fail for, what we are most interested in, which are the really strong, quantum many-body effects. You can think of it as strong correlation or highly entangled, things like that. So not the topic of these lectures, but, that's an important, computational field in itself. So what we really do in the kind of lattice models I'm talking about is basically effective low-energy Hamiltonians that are, supposed to capture the essential physics of strong correlations. So we can study, states and phenomena that go beyond what you can do with those ab initio methods. Okay. So typically we start from, or at least imagine that we start from a tight binding model. So your material has some, band structures, some block states, but you can also construct, one-air states which are localized in space. And if you have this situation where those one-air orbitals are only weakly overlapping, that means basically you can describe the kinetic energy as electrons just tunneling between those orbitals that are connected by the kinetic energy part of the Hamiltonian. But if you have the kind of situation here where the overlaps extend far, then those tight binding approaches are not in practice so useful. They are completely still valid, but you would have to include hopping over large distances. Okay, so once we have these, we can include whatever interactions we think would be important, and sometimes those can be derived using those ab initio methods, and then they give you effective Hubbard kind of, well, this is not yet Hubbard, but we have some hoppings, and then some potential some interaction part of the Hamiltonian. And if we only, if we make the drastic approximation that we only include the on-site part of the Coulomb interaction, then we get what we call the Hubbard model, right? Which has typically would have only nearest neighbor hopping on some lattice, and then an on-site repulsion if you have an up and down in the same orbital. So at that stage, you sort of can forget about where this came from, right? It's just a matter of working with this Hamiltonian, and you think of I and J as sites in a lattice instead of some specific orbitals. Okay, so let me talk about the Heisenberg model, which is the quantum spin model that, in some sense, you start from in many of these studies that I will talk about. So that can be derived from the Hubbard model. So let me ask you a question again. How many of you have seen the Heisenberg model derived from the Hubbard model before? Okay, so several of you, but not everybody. So I will go through that very quickly because I think it's sort of an interesting illustration of how you go from this model to an even lower energy effective model. So this would apply to half filling, meaning you have as many electrons as lattice sites. So then you can see that if the Hubbard repulsion is very large, that will prohibit doubly occupied sites. So you have pretty much one electron on each site. And then you formally think of the limit of very large U, where you definitely have one electron per site, and you treat the kinetic energy as a perturbation to the large potential energy. So now we'll call the U term H naught, and the kinetic part I will call V. Okay, so then if you use infinity, you really have you have a huge degeneracy of ground states, right? You have 2 to the n spin configurations. Only the spin degrees of freedom are left. Nothing can move here. But then we do. So then the energy is 0 for all the 2 to the n spin states. But that degeneracy will be lifted if we consider the leading effects of the kinetic energy. So at least when I teach graduate quantum mechanics, we talk about this. So in fact, I took this from my slides that I used in a course. So in this case, you don't have any first order shift of the energy. So you have to go to second order. And I guess you would recognize this formula. So then pictorially what the formula describes is that you have these degenerate states. You take one of them, and then you see the kinetic energy, which is V, can create doubly occupied sites and empty sites next to those. And to leading order, you only include, you use this formula, so V can only create one doubly occupied site. And then since you will only keep these singly occupied states in your Hilbert space, now you consider these as virtual states, right? So you sum over all of them that don't belong to the degenerate subspace. So now you can think of this entity here, which is what appears between these states here. You can think of that as a Hamiltonian, right? That's your second order effective Hamiltonian, and if we diagonalize this matrix with that Hamiltonian, then we get the second order energy shifts, but that's a spin Hamiltonian because it will describe how the spins interact with each other through these virtual processes, right? So that's how we get the spin Hamiltonian. And a few more details, and this is where I'm going to go pretty quickly. So specifically in the case of the Heisenberg model, all those energy denominators are U, right? The energy of W occupied site minus the one for, none of those. And we can even, since what happens is always V moves an electron and then moves it back to get back to the degenerate subspace, we can even write V squared there instead of this whole summation, but it means the same still, of course. So now we can calculate, we just need to consider, one such case where, we have some site there and it jumps to some site that I call I there. So now, we really have to remember that the spins really are electrons, right? They are the spins of electrons. So we need to write these states as some fermions operating on the vacuum, right? So we create these states, but the spin, depends on the lattice side, right? Up or down. Okay, so then the virtual states, they create, these W-occupied sites. Well, the kinetic energy creates these W-occupied and empty sites. And now to really look at that, we have to have some convention how we order these fermion operators, right? Because when we compute things, we have to take our state and then we have to act, with V squared, which means kinetic energy acting, back and forth, right? This jumping there and one of the spins moves back there. So we have to look at these things, and this is important because it gives us the signs. So eventually you use anti-commutation relations and you get back the singly occupied sites, but it can, there can be there is a sign in front that will be very important. But what's also the case, luckily, is that it doesn't matter where you do that. So you just have to, pick one place where you check it carefully, and it will apply everywhere. So these signs will, you see there's one case, this is like a diagonal interaction because the spin state is the same before and after. The important thing is when you have a spin flip process, so the spin that moved there stays there and the other one goes back. That's the spin flip process. Those come with minus signs, okay? And that's very important. So then, putting everything together, with the partially repeating what I did, you can think of this kind of diagram. You take an up or up and down. By the way, of course, this can only happen if you have an up and a down. You cannot jump an up on top of the up, right? So you have these processes with the factors and signs. And if we then look at those states, what happens to them, we can see that we get the same thing with just a normal spin 1/2 SZ operators and the raising and lowering operators. They do exactly those same things, but we again have to remember what the signs are. So in the end, also, just writing Sx and Sy in terms of the S plus and S minuses, eventually we see that this just becomes exactly the rotationally invariant Heisenberg model. And again, I stress the sign here because if these would have been bosons, we would not get the minus signs here. let's see, yeah, wherever there's minus sign here, we would have a plus if these are bosons. So it's only because they are fermions that we get this rotational invariant interaction, right? So for example, in cold atom physics, people can use bosons or fermions, and if you use optical lattices with bosons, you cannot really get the Heisenberg interaction between them. You get sort of an anisotropic Heisenberg model where the Z component can be antiferromagnetic and the XY component is ferromagnetic. Sometimes that sign actually doesn't even matter, but sometimes it does. I will come back to that later. Okay, so now we have this low energy effective Hamiltonian. So what it means is we had all these states of the Hubbard model, but because of the large U, there's sort of a subset of what we call spin states that are separated from the other states. And the Heisenberg model describes these states here. Yeah.
How is this possible? So your Hubbard model was symmetric with respect to rotations.
That's right.
So how is this possible that if you do bosons, you're going to break this rotation?
Well, because the bosons don't have that symmetry to start with, right? So I'm talking about the spin rotational symmetry, which, if you have two flavors of, okay, I didn't say it carefully. So now we have up and down spins, right? So I could say, okay, let's take red and blue bosons, right? They would not generate this rotationally invariant form of the effective model, right? Okay. Yeah. Yeah, thanks. I should have mentioned that I consider two flavors of bosons then. Anyway, so these states, this picture is a bit misleading actually, because this model, of course, the prefactor is J, and okay, I didn't mention it, but it was on the slides. J is 4t squared divided by U, right? So if U becomes large, J is very small. But of course, this model, if you have n spins, the width of the spectrum is of order n as well, right? So in principle, no matter how big the gap, there will be some spin states, in the thermodynamic limit that will go up beyond those. But that doesn't really matter, because in the end, we are typically interested in physics of only order, when the energy is of order J, not n times J. And those states will be very, far away from, these other excitations of the Hubbard model, so they will not really play any role. Okay, but now we have the Hamiltonian. We still have to solve it, right? And of course, it's not in general possible to solve this model exactly. And I used the square lattice as an example, but of course you could have any other lattice as well. And I will talk about some other cases. So for small n, we can actually diagonalize exactly, and I will talk about diagonalization of spin models a bit later today, or maybe it will be tomorrow. But in 1D, we have an exact solution, right? So in 1D, the Heisenberg chain with nearest neighbor interactions can be solved with the beta ansatz, and we know that it's a quasi-ordered state. It has correlation functions decaying like 1 over distance. I will say more about that as well. In 2 dimensions, we can use spin wave theory to understand most of the low energy physics. And I will not discuss spin wave theory, but I think, even if you haven't heard about it, it's not so important. The important thing is that at 0 temperature, there is, in spite of quantum fluctuations, even for spin 1/2, there is long-range antiferromagnetic order, and the low-energy excitations can be described by this spin wave theory, which you get by mapping to bosons, starting from the ordered state. But it turns out that there's actually some interesting physics. If you don't look at the very lowest excitations, there's a linear, dispersion of the spin waves. If you go up to momenta close to the zone boundary, where the energy is around J or 2J or something like that, there are some effects that cannot actually be captured by any simple theories. If you go to 3 dimensions, there's a finite temperature transition. Of course, here in 2D, the Mermin-Wagner theorem excludes long-range order at finite t, but that's not the case in 3D, so also here you can apply spin wave theory. Now, what I discussed so far was the isotropic Heisenberg model. Sometimes we also look at what's sometimes called the XXZ model, where the XY part has a different strength than the zeta part. And of course, you could make all of them different, JX, JY, JZ. But this one is more common in materials than the case where they are all different. Okay, so we already heard about the Ising model this morning. That's the limit where JXY equals 0. Then it looks like just a classical model. Even though those X and Y components of the spins are still there, they don't play any role in most things that you would do. Yep.
Can you say a few more words about this interesting effect of the J in 2D?
Do you want me to say more about it, or what? Yeah, okay, just quickly. If you look at the spin wave dispersion relation, it goes flat in the zone boundary. So when Q goes from, for example, pi over 2 to pi 0 and so on, there's some cut where the spin wave energy is constant. In reality, there's a dip close to pi 0. The energy dips down. And that cannot really be explained in spin wave theory. But you can look at it numerically, and in fact, I can give you a reference later with many people have looked at it, but we also have me and my collaborators have a paper from a few years ago where we connect that to a precursor of deconfined criticality. That energy starts to dip down, and if you include some other interactions which eventually brings you to a deconfined critical point, you can see that dip becomes larger and larger, and eventually you have a gapless point at pi 0 as well. So that's the anomaly. So I think I will say more about that later. Yes, eventually you will get a transition to a different order state, and that's what we call deconfined criticality. But that doesn't happen in the Heisenberg model, but you can see sort of a precursor in the high energy excitations, meaning excitation energy of order J at certain momenta. All right. Okay, so I looked at, we looked at the simple Hubbard model on a square lattice. You can get the Heisenberg model also in more complicated cases. As long as you have, localized spins on some orbitals, you can, mediate spin-spin interactions. This is the, famous example of the cuprate superconductors and other materials where you have copper dioxide planes. And there, instead of just, these virtual states with W-occupied sites at the same site that we consider, you can W-occupy also these other orbitals here. But it leads to the same kind of interaction as well. And, in those cuprate materials, the J coupling is actually quite strong, around 1500 Kelvin. Now, of course, when we talk about high temperature superconductivity, we are interested in doping these by, charge carriers, which, can mean that we put additional fermions on. You should consider them as holes, but it doesn't really matter. You can think of additional fermions on these oxygen sites. That's maybe the most famous case. But also in that case, one can sort of effectively map this to a one-band Hubbard model with only singly occupied, with only one site per unit cell. So now it's the same situation before, but now you see I have for example, here I don't have any spin at all. So this you can think of, okay, that was the kind of exchange process we looked at, so this can jump back and forth. But here's a hole that doesn't have any W-occupied site next to it, so we can have some fraction of charge carriers. So that's called still the Hubbard model. It's just that you are not at half filling. but also that we can consider U going to infinity, and then you get what's called the TJ model. Very simply exclude doubly occupied sites. So then you can not even have this hopping process as I indicate here, but you could have one here, for example. This electron can move to the hole there. But I will not talk about those models here. There's enough to talk about quantum spin models, although of course these electronic models are probably more exciting in some sense. So, you know, from these copper oxygen layers in the materials, you can actually consider models that are Heisenberg models, but the lattice is slightly different. So if you change the chemical composition of these materials a little bit, you can break up the planes into what's called ladders that are somehow weakly coupled to each other. So you can think of zeroth order approximation as just one of these two-leg ladders or three-leg ladders here, and they have some interesting even odd effects. That has been studied a long time ago. Other things that you can do, which is close to what people can do in materials, is you can replace some coppers by other atoms. For example, zinc, which doesn't have a spin on it, but they cannot move. So this is like static spin dilution. So then that's an example of a disordered system, and you can ask, what happens around a single impurity, and you can also ask about what happens as a function of the concentration. And there are lots of interesting things to look at there. So let me now say a few words about classical versus quantum. So I have drawn this kind of picture here where we just draw a vector, and that you can think of as the classical spin. So what does that have to do with the quantum spin? So we often take the Heisenberg model as a starting point, and we add other things which will change the nature of the fluctuations, can potentially change the ground state. So the two-dimensional model itself, even if it's a quantum model, does have long-range order of this kind at zero temperature, but potentially we can destroy it in some way. But let me just look at this simple example. If you just have two spins, well then any antiparallel spin configuration is a ground state. For example, this one, right? J is positive, so it's an antiferromagnet. But I can rotate both of them, so there's a sort of an infinite number of ground states related by this O3 rotations. But if you look at the quantum spin 1/2, the ground, we only have 4 states, right? And the ground state is the singlet, and there's a gap J to the triplet. So these look quite different, right? But when we go to, you can imagine you study, 2 spins, 3 spins, and so on, and of course you can couple them in different ways. So when we go to n, infinite size, we can develop, macroscopic long-range order that looks like the classical order, but it just is the amplitude of the order parameter is just reduced, because you can think of these spins as wiggling around quantum mechanically. But sometimes we can get non-magnetic states that are easier to understand if you have the singlet picture in mind. Okay, so I will say a few more things about that. Let me mention first about frustration. So by frustration we mean, well, in different communities people mean slightly different things. What we mean in my community is basically competing antiferromagnetic interactions, or it could also be competing ferro and antiferro, but competing in some sense. And that can lead to very non-trivial ground states. So even at the classical levels, if you look at the Ising or XY Heisenberg models, on frustrated lattices, you can get very complicated states, some of which are not completely understood even today. So here, this is an example of a bipartite lattice, which we discussed already, unfrustrated. So let's say this is just the Ising model that we heard about today. But if you put the Ising model with antiferromagnetic interactions on, for example, a triangular lattice, which is an example of a non-bipartite lattice, then you cannot get this kind of ordered state. And I will not talk about that, but you get some very interesting behaviors in this kind of model. So sometimes the classical intuition is useful, but you have to be a bit careful. So going to Heisenberg spins, if we put the antiferromagnetic Heisenberg interaction in a classical triangle, 3 spins coupled to each other in this way, the ground state is actually where they point 120 degrees from each other like that. Well, at least that's the case of the XY. With Heisenberg, yeah, I think it should still be like that. But of course, again, you can rotate all of them. If we look at the quantum spin 1/2 Heisenberg model in this geometry, this is the ground state. So now this is a singlet, a valence bond, as I mentioned before. And since you have 3 of them, you cannot, there will always have to be one unpaired one. So you can imagine then if you look at the Heisenberg model in a classical triangular lattice like here, or if you look at quantum spin 1/2, maybe the ground states can be quite different. Although it turns out, even in that case, there is actually order of that kind even for spin 1/2. But I will not really talk about that. Anyway, let me say something more about this description in terms of valence bonds. So in physics, we mean a valence bond is just a singlet. In chemistry, of course, it has some slightly more intricate description, but basically it's also describing singlets there. So, if you pair up all the spins into singlets, you can do that in a number of ways, and you can actually, of course, then the entire state will be a singlet. If it's just by this we mean that it's a singlet product of the singlets formed in this way. That's, of course, a singlet. But there are many more such ways of pairing the spins up than there are singlets in the Hilbert space. So this is an overcomplete basis. So you can describe any states, but it's not a unique description. So some classes of non-magnetic states are sort of, at least when you try to visualize it, and also in some calculations, in fact, you can work with singlets. So for example, Anderson's resonating valence bond spin liquid would be some sort of sum over all short singlet configurations, for example, here on the square lattice, although Anderson suggested that state for the triangular lattice, which we now know is not correct, and it's also not correct in the square lattice Heisenberg model, but it may be correct more or less if you include some other interactions, that you lose the magnetic order and you just have these fluctuating singlets. Another thing that can happen is that these singlets will line up and form some other type of ordered state. So, to the question earlier about deconfined criticality, is actually describing the transition between an antiferromagnet and this kind of what we call valence bond solid ordered state. So those are useful to think of in terms of these local singlets. Okay, a few words about phase transitions, just quickly. I think everybody knows. So, if we talk about classical or thermal phase transitions, then, as we heard this morning as well, the transition is driven by the competition between entropy and internal energy. When we talk about quantum phase transitions, then we think of zero temperature, and the fluctuations are regulated by some parameter g in the Hamiltonian. So you can also think of that in terms of some fluctuations. If you have some state in mind, and then if you think of a state, you also have some sort of basis in mind, right? So when you think of that, oh, that's my classical as some order, and then you change some parameter which increases the order, the fluctuations in that state and eventually destroys your order. So in both cases, we can have, as a function of temperature in the thermal transition or as a function of some parameter g, we can have continuous and first order transitions. So of course, in the continuous transitions, we have a divergent correlation length, whereas in the first order case, the correlation length stays finite, and you just have a discontinuous transition to another state. Of course, sometimes the correlation length can still grow pretty large, and you can imagine that this curve comes down to a very small value of the order parameter. Then it starts to look almost continuous, and one can perhaps in some cases still see some aspects of criticality, even if the transition is eventually first order. By the way, I think I can just continue, right? And we can skip the break. Is everybody okay with that? Yeah. We have to have a break? Well, we can have a break too. That's fine. So let me just do one more slide. So, yeah. Since you suggest a break, yeah, why not? But let me do one more slide at least. Because it's not quite 45 yet, right? Right, so okay, one additional point is that we are not necessarily just interested in the quantum phase transition, but also the ground state itself, because sometimes we don't know what it is, right? And it can be something very complicated. So let me just give you one example of such a quantum phase transition before we take the break. So if you take our Heisenberg model, which we discussed, that has long-range antiferromagnetic order in the ground state, but now you modify the couplings. So you modulate the couplings. So the red ones here means that the interaction is stronger. We can call it J2, and J1 is weaker. So the coupling ratio, let's call that G. Then if you look at the ground state as a function of G, it looks like this. So when G is 1, we know that we have this Nell order, antiferromagnetic order, also called Nell order on the square lattice. When G goes to infinity, meaning you can think of that as no J1 coupling at all, then you will form singlets on all those bonds where you have J2, and the state is just the product of those singlets. So now we have two ordered states that have sort of a classical picture. I mean, the singlet is not classical, but if you just think of it as a bar there or an ellipse as I have here, you can think of it as some classical object almost, and it can fluctuate. But you should also remember that we could start to get longer valence bonds in some sense, as I explained here. In any case, you should think of this as, okay, now we increase the fluctuations of this classical looking state when we go here, and this one we can also think of as increasing fluctuations as we go here, but because we look at it in different bases. Here we look at it in the spin basis. We have that classical picture in mind. The quantum fluctuations are increasing, but we can also think of the quantum fluctuations of this state as increasing as we go there, because this is a simple product state, right? And of course, it's not completely trivial that there should be a phase transition there. You could think that, well, this antiferromagnetic order just goes down slowly, but that's not what happens, and that was, I think, first proposed by Haldane, probably. At least he had some field theory description of that, claiming that this should just be described by the 2 plus 1-dimensional, meaning 3D classical Heisenberg, meaning O3 universality class. And that has been confirmed by many QMC studies. In fact, there have been some controversies in certain cases because the numerical data sometimes looks very strange. But basically, it's pretty clear that it's an O3 Heisenberg transition. Which of course now, because of the bootstrap, since, I shouldn't mention the bootstrap because we were at a bootstrap conference, right? It can, this critical exponents here have been calculated to a great precision, and they agree with Monte Carlo as well. So this is one sort of well understood case that I will not talk more about here. Interestingly, there's actually a material where one can achieve this transition, but it's in 3 dimensions, meaning the critical point is actually the 4-dimensional classical Heisenberg model where there are log corrections, and one can see those log corrections in simulations. And there's this experiment, where by changing the pressure, you can actually go through this phase transition as well, but I will not talk about that. Okay, so let's take a break. Should we just take like 11 minutes or?
Yeah, we'll start again at 5.
Yeah, all right.
All right. So let's conclude this, the first day with the last lecture by Anders. And I recall you that after we're going to have drinks and food in the patio here outside. Right? So stick around.
All right, welcome back. So let me, before I go to the next slide, I had a question during the break. I had forgotten to comment on the spin gap. So what is that? Well, so, if you have this singlet product state, that you have for large G, you can imagine that the first excited state you get by just breaking a singlet, putting a triplet, and that triplet, can propagate, but is large, the band is very flat, and the excitation energy, between the singlet and triplet is pretty much J. So the gap is J2, I call it here, right? So the gap is J2, but the gap also vanishes as a power law. It's basically the inverse correlation length, right? You heard about the correlation length in the first lecture today. So the gap would be the inverse correlation length in this case. Okay, so one thing is, what's so special about quantum critical points? So now you saw in the previous case we had a 2D Heisenberg system and its critical point maps onto the three-dimensional, and you can see that through the path integral. That's what Haldane showed. So then you think, well, okay, we just can study the classical model and we get that critical point. That's true if that's your only interest. But there are other things here which are very special for quantum models, and let me give one example which is from quite some time ago. But it's the 2D, the kind of system I showed you on the previous graph. What happens if you put temperature there? So we can only have a Nell order in 2D in this isotropic system at 0 temperature, so that's the thick line here. And on that side, we have this non-magnetic, also called quantum disordered state, because it's disordered by quantum fluctuations, if you think of it, coming from that direction. There's an energy scale of that, which is, the spin gap that I mentioned. Now, what happens on this side at finite T? Is there anything interesting? Well, it turns out that if you are at low temperature, then even some aspects of the system behaves really classical, like a classical 2D system. So if you look at the classical 2D system as a function of temperature, the correlation length diverges exponentially as you go to 0 temperature, and that happens here too. The only difference is that the factor in the exponential is renormalized, so there's a stiffness constant that enters there, which is like a helicity modulus of the spin system. And that's the relevant energy scale here. So that's called the renormalized classical region. Well, I explained them here too. So the most interesting here is that you have what's called the quantum critical region, or sometimes people call it the quantum critical fan, where if you do some experiment or numerical simulations, you see the influence of this critical point even quite far from the critical point. If you go to normal classical phase transitions, to really see critical behavior, you have to go really close to the critical point. And the same would be the case if you want to study the criticality by crossing here. It's only when you come really close to that point that you see, the power law scaling of the correlation length and so on. But you can go up to quite high temperatures until, some lattice effects kick in. This comes from continuum field theory, and that breaks down at some high temperature where basically the correlation length becomes of order 1 lattice spacing. But in this region, on either side of the transition and up to quite high temperatures, you can have basically, power law scaling. And in this case, you have these, very definite forms which have to do with the fact that the dynamic exponent here is 1, which is, means that it's a conformal field theory. Then, one can use some aspect of finite size scaling to derive these by, this point is described by this 3D classical system. Make it 2 + 1, and the one direction is your inverse temperature. Then you can do finite size scaling in that length, which we can call L tau, and then you get these behaviors, and this was shown in this paper and other later papers. I will show you some other examples of this later, and this can really be experimentally important too, because in experiments you can really not go to 0 temperature, right? But you can go to low temperatures, and maybe you don't need to even go as low as you might suspect to see the influence of the critical point. So this is something that you don't have in classical systems, because it's really the 2 + 1 dimension. It's the additional dimension that kicks in. Yeah.
In classical critical system, there is this story about universality, which I guess you still have at this temperature point.
So what did you say about the critical?
Universality.
Yeah, the universal, yeah, exactly. So this is a universal critical point which is dictated by your symmetries, right? So it's the O3 point. Now you can have other cases, for example, deconfined criticality, which I will talk about later, where you have some other universality class there.
Above in this file, you have any universality?
Oh, yeah. So no. So the behaviors that you see here. Okay. So the examples I gave here, I sort of realized when I made this slide as well. These are not so exciting in the sense that this only depends on z, and z is 1. But I can mention one other case. If you go to I don't know if you are familiar with NMR, nuclear magnetic resonance. You can measure some spin relaxation time, and it turns out that that relaxation time, which is called 1/T1, you don't need to care about why, that should go like the temperature to eta, the anomalous dimension. So that would be a way to check really what the critical point is beyond just the value of z, which would enter here. And in fact, I will talk about that. I don't know if I will talk about it during the lectures, but in the conference week later on, I will give a talk where I mention some recent experiments. Maybe I will mention them a little bit here as well, where we actually seem to see something like that for something that may be deconfined criticality. I think there was some, yeah, please. Yeah.
So if I take a horizontal slice at non-zero t,
Yeah.
What happens to the ground state as I enter the quantum critical region and as I exit the quantum critical region?
Okay. So of course, here it's not the ground state, but you go from this state which has a very long antiferromagnetic length. The correlation length is exponentially here. So even if you are not at very low temperature, maybe your correlation length is 100 or 1,000 lattice spacings. So very quickly, there will be a crossover where that basically, those strong correlations instead develop some power law character, but only up to some correlation length, which in this case is 1/T. And then when you cross over there, the correlations just become exponentially decaying. Yeah, please.
So can we determine the shape of the phase boundary?
Oh yeah, so I should stress that these are not phase boundaries. They're called crossovers, meaning that there's just some very rapid or it's not clear unless you do a calculation how rapid it is. So this is the spin stiffness at 0 temperature, which sets the energy scale of the high temperature crossover. So this can be computed using the kind of methods I will talk about later on. So you can draw a line here, but you cannot say exactly where the line is, because it's just that you go from some sort of behavior to another behavior, and it's always sort of smooth, but it can be rapid, right? And in this case, it's like, okay, you look at certain quantities, and at some point you sense that there's a gap. So certain quantities, for example, the magnetic susceptibility will just start to drop to 0. For example, if you measure or do a calculation of the magnetic susceptibility as a function of t, it will do something like that. It will drop very quickly to 0 when you enter that, when you cross that boundary, which is not completely sharp because, you know, where do you put the line, right?
For example, the computation of two energy scale.
Yeah, you can, yeah.
Then what is the energy? What are the energy scales
Okay,
at
the
the
energy
crossover?
scale is the gap competing with the temperature, right? So the point with the quantum critical region is that there's only one energy scale, which is the temperature. But in this case, you have, you know, away you have two energy scales. You have the temperature and then some macroscopic energy scale of the system, which is not the microscopic energy scale, it's the macroscopic, right? The microscopic energy scale here would always be, you know, J1 or J2 or something. It would not go to zero. But the macroscopic energy scales will drop to zero there. And you only have one relevant energy scale here. So, good. All right, so let me go on. Now, let me talk about another model, which is a model that I'm, you know, currently very interested in. So I like to talk about it, and I think it's really a good example of theory and how it connects to experiments. So this is the Shasta Sutherland model, an illustration thereof. So we have the Heisenberg model with the black lines. You can think of nearest neighbor interactions between these spin 1/2 degrees of freedom. But then there's another coupling, which we call, you know, J prime, which, you know, is not, it's a next nearest neighbor interaction, but only between some of the next nearest neighbors in this particular pattern. So you may ask why somebody looked at this kind of model. Well, Shasta and Sutherland, they did it in 1982 or something like that. And what they were interested in were, you know, models that had some exact ground states. So there are some, you know, there are some examples in one dimension before that, and I will also talk about that one likely tomorrow. But they wanted something in 2D, and they came up with this model. So both these interactions are antiferromagnetic, so they are frustrated in the lingo that I explained before. So it turns out that, you know, if you form singlets on these red bonds, you just draw your, you know, dimers with these ellipses that I showed before. You say, okay, every spin belongs to one such bond, so you can form a singlet, and then you have a singlet product state. It turns out that that's an exact eigenstate of this model, no matter what J and J prime are. It's always an exact eigenstate. And, you know, it's very easy to test, right? You can just operate on that state with your Hamiltonian, and you will see that that's the case. And it turns out, so that's what they showed. And then they said, well, so that's always an exact eigenstate, but it's not always the ground state. And then to see, you know, for if it's ever or for what ranges of J and, well, here I say J1, that should be J perp. It turns out, you know, numerically, you know, already for, you know, long time ago, people have known that up to about 0.68. So this J is, you know, we turn on the nearest neighbor interactions, and eventually that exact ground state becomes an excited state. It's just a level crossing. But what happens then, you know, after that Shasta and Sutherland did not know. But people have looked at this numerically for a long time, and I don't show all the references here, but this is a relatively recent work by Frederick Mila and Philip Corbot. I think I state the reference at some point. So what do you have? You have the unique singlet ground state up to about this point. And then you have another state, which is, you know, a little bit similar to those, you know, valence bond solids that I showed before, where singlets lined up. But in this case, you can think of a plaquette as, you know, plus, or it could be minus as well, but in reality, I think it's plus here. If we draw a plaquette like that, we mean two resonating pairs of parallel singlets. And what this shows is just the singlet density on the bond. So they have used a numerical method, which I will mention, to compute the singlet density on those bonds. And here, there are really singlets only there. Here you can see there's a higher singlet density on some of the plaquettes, and that's because you have this kind of valence bond resonating state there. But here you can see that you have actually symmetry breaking. You break a twofold symmetry here because these stronger plaquettes could also have formed on these other empty squares. So you have a twofold degeneracy there, and you have a phase transition where that symmetry is broken. And then if you go even higher to about 0.77 or maybe a bit higher, you get the normal Nell antiferromagnet that I talked about before, which clearly you have to have in the limit when this goes to infinity, because if J prime is 0, you know, the red ones here, you just have the same model we talked about before. Okay, so that's an interesting model, and so as I mentioned, Corbots and Mila, they did this with what's called a tensor product kind of variational ansatz, which is in principle a controllable variational ansatz, and I will not talk in detail about this method, but maybe tomorrow or whenever it will be, I will at least tell you roughly what that means. For now, it's something that is, you know, should be good, but not exact, because these tensors, you know, may not be big enough. Anyway, so what they claimed is that, you know, this transition here between plaquette and Nell phase, that could, in principle, be some kind of deconfined critical point, okay? But here they claim that it's first order. But, you know, more recently, there was a paper by these people here. I guess Sashdev is a co-organizer of this meeting, but will he be here later maybe? Or? Right, good. So they claimed, you know, using DMRG, which, you know, you may know or may not know what it is. I will also explain that very quickly later on. They do claim that it's actually a deconfined critical point with emergent O4 symmetry, you know, at the transition between these two states. Okay, but the story gets, I think, even more interesting, although, you know, maybe it's still controversial. So some work I did myself with my former student, Ling Wang, who's now a professor in Zhejiang University in China. So she is an expert on DMRG and also on exact diagonalization that I will talk about. So we have two papers, and I will later on talk a little bit more about it, what we see. But for now, we believe that there is actually yet a fourth phase here, which is a gapless spin liquid phase. Let me not say so much more about it now. But okay, so this is a model. But why people are really excited about this model, well, apart from these, you know, theoretical questions, is that there's also a Shasta-Sutherland material, which was not made by Shasta and Sutherland. Well, they are, you know, certainly great people, but I think they don't, you know, construct materials in the same way as they construct exactly solvable models. But somebody else discovered in the 1990s. I think it was discovered first by a Japanese group, but many people have studied it since, strontium copper borate, which consists of layers, again, of where there's some copper atoms. I will show some other picture later, more realistic. But you see here, there's an animation that I stole from the web. I don't know who made it. Everybody uses this picture, I think, where you see that we go from, you know, the Shasta-Sutherland lattice to something that looks a little bit different, but is equivalent in terms of the couplings. And that's how the material, the layers in the material looks like. But basically, there are two couplings matching the Shasta-Sutherland Hamiltonian. And it turns out that in under atmospheric pressure, the coupling ratio that people have estimated in various ways is about 0.6. And if you recall, you know, close to this phase transition here, but still in this singlet dimer phase. And in fact, you know, a lot of experiments are completely consistent with this dimer kind of phase in the material. So then it sounds like, well, maybe not so exciting. Well, it becomes very exciting when you add a magnetic field, and you can see what's called magnetization plateau states, and it's a lot of experiments have been done with those. But there's something else that is more recent and very interesting. So it turns out when you put pressure on this material, then these couplings grow. You compress the material, but they don't grow at the same rate. One grows faster than the other one, in such a way that this coupling ratio actually increases. So then you could potentially actually get into this other phase. And in fact, this is what happens. So this is some figures from some recent experimental paper that I was myself a co-author on, so that's why I like to talk about it, but not only because of that, because I think it's a really nice example and probably one of the best experimental opportunities to look at the confined criticality and things like that. So you see what happens here. As a function of pressure, this is, by the way, more what the material looks like. You can see these different atoms and the layered structure and so on. As a function of pressure, just looking at the specific heat and having some input from some neutron scattering experiments that had been done before in terms of, that you can really enter this plaquette singlet phase. There was like one point somewhere where a neutron scattering experiment indicated that you no longer have this dimer structure, you have more something like this plaquette structure that is illustrated here. But the phase boundaries were not known. So these, my collaborators in China, they measured the specific heat. And you can see in some cases it's just a bump, and this is exactly what you expect in this dimer singlet state. But in some cases you see there's another peak here. And that's how we can map out these phase boundaries here. And again, using some other information, which I will not get into now, we believe that this is the plaquette singlet state, and this is the antiferromagnetic state that you have in the Shasta Sutherland model. So you can actually, get these quantum phases and transitions. Now, in some very recent work, also with Chinese collaborators that I worked with, well, I mean, they did the experiment, but I was involved in the theory interpretation a little bit. So they did NMR, and that was one aspect of this. It looks like with a magnetic field, one can actually come, if you sit somewhere here and include a magnetic field, and I will talk more about it later, it looks like something like deconfined criticality, like that. But for now, let's just say that this is a really good illustration of a model and material and how we can work together. Yeah.
So what's the path?
What? Oh, you mean this one? Yeah. Oh, okay. So this is the location of, yeah, good point. This is the location of this big peak here, which is not a phase transition. It's just a sort of, again, a crossover behavior. The data points are from the experiments, and the curve is actually from fitting to the Shasta Sutherland model, using a calculation on a small lattice, but maybe big enough lattice that it actually makes sense, but it fits sort of extremely well. So in that way, by fitting that line, you can in principle see what pressure corresponds to what value of this coupling ratio. So that's the point of this line. Say again? Okay, so that's the location of the big peak. The second peak, maps out these transitions here and here. And that peak is very small, and why is that? Well, because the correlations build up in the system and sort of eat up a lot of entropy. So the weight under C over T, that's the entropy change as you go through the transition. So there's not a lot of entropy to consume anymore at that temperature. That's why these peaks are so small. Yeah, please. Well, okay, maybe they are not exactly the same, but I think it should not matter here in the sense that you know, the lattice should just be an irrelevant perturbation of the low energy, you know, theory anyway. So as long as the couplings match and the phases match, I think it should be okay. You know, I never remember the names of these symmetries, but you can sort of see, right, you know, how you can translate and reflect and all those things. So it's definitely known and mentioned in some of our papers, but I never remember the names of those point group symmetries. Sorry. Yeah, that's exactly right. So so when we do the exact diagonalization, we use those glide symmetries as well. So it definitely has that. Yeah. So I think they should match. I don't see why not. I think they must have the same point group symmetry. Yeah. Okay, so let me say a few words about deconfined criticality, because you know the term has been thrown out around a few times already. So, you know, the story sort of didn't really start in 2004 by these people, but they made some further progress on something that had been discussed for a long time, namely exactly what can happen if you manage to destroy the Néel order in an antiferromagnet. And it had been known, for example, by Subir Sachdev's and others, Reed and Sachdev, 1 over n calculations. You know, you increase the symmetry group from SU2 to SUn of the spins. Then you get this kind of valence bond solid for large n. So that was one, you know, potential other state that you can get. And then you can imagine that you could get that also with SU2 spins if you just add some other interactions. And then people describe that with the field theory. And it was more or less known how to do that, but you know, let me not talk about it. I think somebody else will talk about the field theory probably. But they made some sort of, well, you know, partially I think they were stimulated by some numerics that came out a couple of years before that looked like you could have such transitions in some model systems. And then they did some additional, you know, large n calculations. And the claim was that you can have you know, a continuous transition between these two phases that break unrelated symmetries, which would be a violation of one of the lambda rules that tells you that in that case you should have a first order transition. And you know, the theory involves the role of topological defects and so on, but let me not get into that. And of course, you know, deconfinement of spin-ons. But you know, people have been, of course, very interested in seeing this experimentally, and I think the material I showed you before would be the most promising. I don't think anybody can say that we have seen deconfined criticality in a real material yet. But another thing we can do is to try to cook up some lattice models that have the same physics. So for a long time, people had looked at this kind of physics also in frustrated spin models. For example, you take the square lattice with coupling J1 and J2, but now you put the J2 everywhere on all nearest neighbors. But that model has what's called a sign problem in quantum Monte Carlo, which is the method that you can reach the biggest systems and draw the most clean conclusions. I will talk about such calculations later. So people were restricted to very small lattices. But then we can look at what's called JQ models, which don't have sign problems, and they allow us to use QMC on very large lattices. So that will be something I will talk more about later. This is sort of still the introductory part. So, the Heisenberg model is basically just the sum of singlet projectors. So this is the singlet projector on two sides. And if you put minus in front of that, then you have the Heisenberg model. You sum it on all all the bonds. So now we can combine, for example, the J term and what we call the Q2 terms. Here I just call them Q. So we start with the Heisenberg model and add this kind of interaction. And you can sort of naively see that that would favor this kind of columnar order, especially if you go to what we call the Q3 term, where these singlet projectors are lined up really in columns, and you can do Q4, Q5, and so on. So you can imagine that those would favor, this kind of state. But there's no sort of reliable approximate calculation even for, well, one can do all kinds of things, but nothing is really reliable until you go to quantum Monte Carlo. So we do see that kind of transition. And it appears to be continuous, but most likely it's actually very weakly first order. And I think I will talk about the fact that when we go to larger QN terms, more of these singlet projectors in a product, we can see that the transition becomes more and more strongly first order. So maybe for the JQ2 model, it's still not completely clear, but most likely it's weakly first order. But the correlation length is so long that we believe that we can extract exponents and so on, because the discontinuity, for example, if you look at the jump here, it may be so small that it only kicks in. You only see it when you go to really huge lattices. Right, so that will be something I will build up to talking more about once we have talked about how to do QMC simulations. Now let me, as the last part almost of the introduction, mention some random models, disordered models. So here there's an interesting material where you can mix tellurium and tungsten in a way. So this is also a layered material. So it also has these copper sites, the black dots here. But now there's something in the middle of these plaquettes. And that can be either tellurium or tungsten. And it turns out that those, in this case, mediate the exchange interaction. You don't get a lot of direct exchange. You have to do a super exchange mediated by the ion in the middle. And interestingly, which one you have there will dictate if you have mainly J1 interactions, like in that case, or mainly J2, like in that case. And then it turns out that one can mix them. So you can prepare this at basically any x, and then you will have a 2D lattice where some plaquettes have J1 and some plaquettes have J2. And this will be a randomly frustrated lattice. And this is what is seen experimentally. You have a Nel antiferromagnet of the kind we have discussed before in the square lattice when you are in this situation here. If you are in this situation where x is 1, then all the couplings are like that. And then that actually gives a columnar antiferromagnetic state. So the spins are lined up not in the checkerboard pattern, but in columns like that, and up, column down, and so on. And of course, you can have those in, rotated as well. So the interesting thing is what happens in between here. Okay, so one can actually model some, so this is some modeling we did based on just a classical Heisenberg model, which you wouldn't really be expect to be that good, but maybe it could say something about these phase transitions. In particular, the antiferromagnetic order vanishes very quickly. And I will not go into the details here, but there's actually a very interesting mechanism for that. It turns out that these J2 bonds have a very strong effect on the Nel state that you can understand even classically. And in fact, if you have just one layer, you will not have any order for any finite concentration. But when you couple layers in 3 dimensions, you get phase boundaries, and they agree pretty well with what you get experimental. But the really interesting thing is what happens here in between. So there what we believe is that you get something that we call a random singlet state, which is also something that has a long history, especially in one dimension. It's well understood what that means. In 2D, it has not been so clear what the corresponding state is. But at least we have found one way to realize such a random model that has a ground state which can go from null order to something which doesn't have any order. And it turns out to be a very interesting state, which is actually like a critical state. It has power law correlations in an entire phase. So I will talk about, and that we can do with these JQ models as well by making the interactions random in some way. All right, so now I talked about some sort of materials motivated models, and I also mentioned, confined criticality, which is, something that we can really do numerics to connect to, ongoing and controversial in some aspects field theory work. Let me also mention about quantum emulation. So by a quantum emulator, we again mean something like a physical device that can mimic a quantum many-body system. And in most cases, that would mean that we make some qubits, which are two-level systems, and they interact with each other in some way. Preferably in some way that we can control and sort of program like an analog computer. So examples, Rydberg atoms, I will not mention them, but those are highly excited atomic states that you can make arrays of and mimic all kinds of things. Also, there are devices with coupled superconducting qubits, so let me say a few words about those. So there's this company D-Wave in Canada, and they have now already made several generations of their computer, which in this most recent version has more than 5,000 programmable qubits. So this is what their chip looks like. I think this is like 1 centimeter square roughly, and you see there's lots of leads going into it. And the actual machine looks like that. Everybody can buy one. If you have $10, $50 million or something like that, of course it has to be cooled to some super low temperature, and that's all hidden here to look nicer, I'm sure. If you want to sell it, it has to look nice. So what is the machine doing? So the machine is doing what's called quantum annealing. So this is something where you have a Hamiltonian, which you consider as having two different terms, and here I call one of them classical and one of them quantum. Of course, as I mentioned already, which one is classical and which one quantum depends on the basis you look at. It's like something that's diagonal, you just call it classical, roughly. And in this case, there's a parameter S, and S should be between 0 and 1. So if S is 1, it's all classical. If S is 0, it's all quantum. So in the D-Wave device, the classical Hamiltonian is an Ising model, but with couplings that you can basically program. The couplings are not completely general. They are limited to what they call the Pegasus lattice. So here these orange dots are the qubits, and the blue lines, and I guess the green lines as well, they show how these are connected to each other. So within that connectivity, you can think of this Jij being between -1 and +1 in a way that you can control. And then, the machine has quantum fluctuations in the form of a transverse magnetic field. So this is Z, and this is X, right? So that transverse field can be turned on and off, through this S. So this, in annealing, S goes from 0 to 1. over some time. You know, in this particular way, I think the way one is, you know, one coupling is turned on and the other one turned off. So, okay, here it is, right? So A is in front of the quantum term, so that's this one is turned off and the other one is turned on. That's just dictated by engineering. It's probably hard to do it in some arbitrary way. But the black line here indicates the temperature. So, you know, it's cooled to some temperature, and in these energy units, that's what the temperature is. I forget what that is, some millikelvin, tens of millikelvins or something. And you see, at least, you know, when everything is well above that, it should sort of be behave quantum mechanically, at least over some time. So what they do is they change S as a function of t, and you know, the total time from S goes to 0 to 1 can be between a few nanoseconds up to milliseconds. So you can actually already, with what they have available today, you know, even, you know, as noisy as it is in some sense, you can actually study annealing dynamics. And that actually motivates theoretical studies of these transverse field Ising models. There are also some materials that are described by that model, but I will not discuss that. Okay, so that's blank, so that means that the introduction is completed, so now I will change to another presentation, but maybe there are some questions about this introductory motivation. Yes, please.
So in the simulation of random JQ model,
Right.
why is there an asymmetry between x goes to 0 and x goes to 1? So the...
Okay, so this is, you know, I didn't mean to say that the random JQ model can mimic this material. It cannot. So to study this material, you would have to, you know, use, you know, the actual model with J1 and J2. So the JQ model, you know, as I showed in the previous slide, has, you know, completely different interactions. But what we can do is we can make, you know, the Q random. So we can put Q inside here and give it, you know, a location dependence as well. And we can do the same with J. So we can do random Q, random J, or both of them random. So then it turns out that since the valence bond solid breaks a discrete symmetry, right? If you put any disorder, it's known from what's called the Imre-Ma argument, I think it's called, that above a dimensionality that turns out to be 2, you will form domains. So the valence bond solid will break up into domains, and that state, which has all these domains, actually also have unpaired spin-ons appearing, and those spin-ons interact with each other in a way which gives rise to this really interesting magnetic, non-magnetic, but you know, critical state that we argue is sort of described by the same fixed point as what you have in the material. We cannot prove that, but we have some evidence from the experiments, as well as from calculations of actual frustrated J1, J2 models, that they are the same. But I will try to discuss that a little bit more later. All right. Okay, so maybe I jump to the next. Oh yeah, we should stop now, exactly. Yeah. I was thinking it's until 6, but it's, yeah, okay, then it's perfect, yeah.
All right.
So this took only twice as long as I had planned, right? Because I had planned the introduction for one lecture, but I knew that, so it will be okay. Thank you.
All right. Thanks.